In example 12, we're going to be solving an equation using the one-to-one property of logarithms. Using the one-to-one property of logarithms to solve logarithmic equations. For any algebraic expressions s and t and any positive real number b where b cannot equal 1, if we have the log of base b of s, which is equal to the log of base b of t, if and only if s is equal to t. So kind of similar to when we had the same base, we can let the exponents equal each other. In this scenario, since we have the same base and the logarithms are equal to each other, then we can say that the arguments, in this case called s and t, are equal to each other. Now note, when solving an equation involving logarithms, always check to see if the answer is correct or if it is an extraneous solution. So in order to solve for this, if we're given an equation containing logarithms, we're going to solve it using the one-to-one property. Step 1, we're going to use the rules of logarithms to combine like terms. So if necessary, so that the resulting equation has the form of a single logarithm on one side of the equation and a single logarithm on the other side of the equation. So sometimes you may have to condense to get one single logarithm on one side and one single logarithm on the other side. Number 2, we're going to use the one-to-one property to set the arguments equal to each other. And then 3, solve the resulting equation for the unknown. So in this example, we have the natural log of x squared, which is equal to the natural log of 2x plus 3. So in step 1, we wrote the equation. And then we're going to use the one-to-one property of the logarithm. We have one logarithm isolated on this side. We have one logarithm isolated on this side. And the other important information is they have to have the same base. Now, since they do have the same base, which is e, then we can set the arguments equal to each other. So in step 2, we have x squared, which is equal to 2x plus 3. Now, we have a square, and we have 2x and a plus 3. Well, we can't really solve this unless we bring all the items on one side of the equation and set it equal to 0. So to get 0 on one side before factoring, we're going to get x squared minus 2x minus 3, which is equal to 0. And then we can factor. So when we factor, we got negative 3 and negative 2. The two numbers to multiply to get negative 3 and add to get negative 2 would be positive 1 and negative 3. So factoring using FOIL, we get x minus 3 times x plus 1, which is equal to 0. So now if a product is 0, one of the factors must be 0. So we're going to solve for x. So we're going to set x minus 3 equal to 0, or x plus 1 is equal to 0. So when we solve for both of them, we get x equals 3, or x is equal to negative 1. Now, both of these can be solutions. Both of them are possible where they're not solutions, or it's possible that one is a solution and the other one is not. But you always need to check. So if you look over here at step 6, we're going to check our solutions. So one of them was x equals 3, and we're going to plug it into the original equation. So we have the natural log of 3 squared, which is equal to the natural log of 2 times 3 plus 3. Well, 3 squared is 9, so we have the natural log of 9 on this side. Well, 2 times 3 is 6 plus 3 is 9. So we have the natural log of 9. So we know that x equals 3 is a solution. On this side, x is equal to negative 1. Now, remember that in other examples, we saw that whenever a number is negative of an exponential function, it may not be a solution. But in this scenario, if we plug in negative 1, when we square it, we're going to get positive 1. So we get natural log of 1. On the right side, 2 times negative 1 is negative 2, but plus 3 is positive 1. So the natural log of 1 is equal to the natural log of 1. So that's also a solution. So there are two solutions, 3 or negative 1. And again, the solution negative 1 is negative, but it checks when substituted into the original equation because the argument of the logarithm functions is still going to be positive.